Alrighty, we'll go ahead and get started in just a minute here, but just a couple logistics before we do get started. There is a Q&A attached to the webinar, so feel free to chat any questions you have throughout the webinar. I have a colleague on the line. He's happy to answer your questions. He'll chat back. I can also answer some questions live towards the end of the webinar if there's anything that I think should be addressed for the whole group. Also, if you do have the option, generally the best way to view the webinar is this side-by-side mode. I do have quite a few metal parts with me here today that I'll be showing off throughout the webinar. I also have my overhead scope here, which you may have seen me playing with to show some parts in high detail. So if you do have that side-by-side mode, that generally is the best way to see the presentation. I think a few more people will be trickling in, so we'll just give it a couple more minutes here, and then we'll go ahead and get started. Alrighty, let's go ahead and get started. Today we're going to be talking about additive manufacturing for heavy industry. So a quick overview of the agenda today. We'll start by looking at what some of the challenges are in the heavy industry and what some of the additive manufacturing solutions are to those challenges. We'll talk a little bit about the promise of metal 3D printing and how those help to alleviate those challenges as well, specifically to heavy industry. We'll look at what some of the current challenges are with metal 3D printing and how Desktop Metal solves those with this, additive manufacturing based on metal injection molding, which is the approach that Desktop Metal took towards 3D printing. We'll look at a bunch of different applications. We'll look at a bunch of different parts that I have with me here today, and then we'll look at some case studies and talk about some customers, how they're using Desktop Metal products and how they're adding value. So quickly, Desktop Metal was founded in 2015 with the goal to make metal 3D printing accessible for engineers and manufacturers. And what I want you to take away from this mission statement is this idea of accessibility. Really, metal 3D printing had been around for a while, but Desktop Metal was really founded with the goal to make it accessible to the everyday engineer, to the everyday manufacturer. We have 4 printers today in the market. We have our fiber printer on the far left. That's that composite machine printing things like carbon fiber, fiberglass, PEEK, and PEC materials. Won't be talking too much about that today. We have the Studio System, which is the machine that I have behind me here. That's our really office-friendly metal 3D printer. It's great for prototyping, one-off parts, low volume, a lot of tooling applications. It's probably the easiest way to make these very, very, very complex metal parts, safely in your office. My desk is just across the room over here, and this printer, runs all day long right next to my desk. So super, super safe, super, super accessible, like we mentioned. We then have the Shop System. That's our, it's our binder jetting machine. One of our binder jetting machines allows you to produce, hundreds or thousands of parts per day or per week, allowing you to create, kind of scale up those volume. When you want to go from maybe 10 or 15 parts per week up to hundreds or thousands of parts per week, you can move to the Shop System and really crank up that volume. And then Production System even more so. When you really, really need to produce parts in high volume, the Production System is really allows you to actually mass produce metal parts with 3D printing. So like I mentioned, today we're going to be talking about the Studio System, and then we'll be talking about the Shop System and the Production System, but I'll mainly just be addressing those as binder jetting because they have somewhat similar technologies. They both work on a binder jetting basis. We've been shipping systems for a few years now. We're shipping, all over the globe, 49 different countries. So depending on where you're watching from today, there is a reseller nearby, there is a partner group nearby, there's a printer nearby, really global, shipping globally. And looking at customers, it's important to know this technology is being utilized, really across the board, across a lot of industries. But one thing I want to mention, This technology is being utilized by some of the largest companies in the world, like the Toyotas and the Googles of the world, as well as some of these small companies you've never heard of. These small one or two person manufacturers, these small design studios, the mom and pop machine shop, because these systems are really so accessible. The price point is so accessible. The ease of use is so accessible that it's making it possible to put these machines into these, they're adding value to the largest companies in the world and to some of the smallest companies in the world. So really, just bringing up this idea of accessibility that, we're really targeting here, adding value everywhere to companies all over the globe and, from all different sizes as well. Looking just at heavy industries, we'll talk about some of these companies today, but I'm sure you recognize some of these names if you're familiar with the heavy industry. Companies like John Zink or Owens Corning. Some military organizations as well as Lincoln Laboratories. Doing lots of work in the heavy industries, and I think you'll see that today as we talk about parts and look at some of those specific applications. So, what are some of the challenges that we're hearing constantly when we talk to people who work in heavy industry? One challenge that we hear a lot, and we hear this across a lot of industries, is this challenge of low volume production. When you're producing parts in low volume, maybe you only need a handful, maybe you only need one, but these inexpensive mass production methods that are going to require a lot of tooling are not possible. So you can't do things like casting or metal injection molding, forging, stamping, extrusion, even plastic injection molding for plastic parts. They're just not possible when you're producing parts in low volume because the tooling expenses are too high. So this is a challenge we're hearing a lot, the ability to produce parts in low volume. The test to iterate on multiple different geometries, all while doing this in parallel. Especially when we're working with complex geometry, it may be difficult and expensive and a long lead time just to get one of a component. But now maybe we want to be able to do some design iterations. We want to do some prototyping. But the ability to do all of this, in parallel is something that's very challenging. In heavy industry, we're seeing these massive machines, thousands or hundreds of thousands, even millions of parts. So managing these very complex bill of materials and assembly procedures is a challenge. You have whole teams, who are working around assembly procedures or working around bill of materials and supply chain. It's very, very, very difficult to manage these very large assemblies and ensure everything is being put together correctly. So, another challenge that we're seeing. This one, you see in almost every industry as well, but, CNC shop bottlenecks, foundry lead times, and these NRE costs or non-recurring engineering costs. This is a challenge for a lot of people where, you need a part, but the shop is already so backed up, it's going to be 6 to 8 weeks. 3 to 4 weeks for a machine part is pretty common. We hear that all the time. That, if I need a part created, it's going to take me far longer, and that's really limiting my design. It's limiting my ability to, deliver my end use machine to my customer. And then of course, aftermarket parts. Heavy industry, especially, we're making these very large machines. They're expected to, be in production for a long, long time. They're supposed to operate for a long, long time. So, if a part were to break, if a part were to need to be replaced, it needs to be done quickly. It needs to be done affordably. So these aftermarket parts can be quite difficult to produce, especially if that part was originally produced with one of these mass production methods like casting, metal injection molding, forging, or stamping. Because, the tooling no longer exists, that it's very difficult and very expensive to reproduce those parts. So how does additive manufacturing help with these challenges? When it comes to low volume production, additive manufacturing, of course, there's no tooling required at any point during the process. This means that our part costs are going to stay the same if we need, one of our part or if we need 10,000 of our part. This means that, this is makes low volume production very, very easy because, there's no upfront tooling expenditures. You don't have to invest in fixturing for machining or, or molds for, casting or die casting or any of those operations. Your part cost is very clear from the beginning and it's not going to change. In terms of, iterating on multiple complex geometries, we can now rapidly prototype parts, from the comfort of our office. The printer behind me here, when this webinar ends, I'll load up, maybe this roller screw that I have here. It'll finish in the morning and I can load up an impeller, the same day. Or, I can put multiple of these on the same bed together, allowing me to produce lots of complex parts, all very, very, very easily without having to go outside of this room even. Also, now that I'm actually able to prototype in metal, I can actually test these parts, for their function, not just their form and fit like we see in plastic. We can do high loading, heat, corrosion environments. We're actually able to test the geometry to see how does this perform in the assembly, not just its form and fit like you would with plastic to see, does it fit into my machine? In terms of bill of materials, we're seeing lots of assembly consolidation, assemblies going from 100 parts to one, 5 parts to one. Generally we're able to eliminate lots of fasteners because we're able to consolidate parts just into consolidate many assemblies into just one single part. So many parts today are designed for their manufacturing method rather than their specific, idealized geometry. But with 3D printing, we can get much closer because it doesn't add a lot of cost for us to consolidate some of that assembly into just one part. Looking at CNC shop bottlenecks, of course, this machine, you're still going to have to, you have to wait for the parts to print it, and you have to wait for the furnace to print, and we'll talk about that later. But, really what we're seeing is a lot of teams that are able to take manufacturing into their own hands. They don't have to rely on a different team. They don't have to rely on an outside machine shop. They're able to control the printer. They're able to control the queue. They're able to control, the print jobs. This allows them to prioritize themselves. They are in complete control of the parts they're getting out of the system, allowing them to really, queue the machine better and really just take this, fabrication into their own hands, which gives them a lot of freedom. For aftermarket parts, this machine's, quite fast. And like we mentioned earlier, there's no tooling required, so part cost is going to stay the same. This means that, generally we don't need to warehouse a lot of components that can be printed. Rather I can just pull the file, throw it on the printer, in a couple of days I'm ready to ship it out to the customer. This is, excellent for parts, that may have been cast originally. We'll look at some examples of that today, specifically this part, a little spoiler, but, parts that were originally cast maybe 10, 20, 30 years ago, but, those foundries no longer exist, or that tooling no longer exists. We can simply pull the part file, throw it on the printer, we're ready to ship it out to the customer in just a few days. So, what are some of the parts we're seeing in heavy industry? We're seeing a lot of, and I should have defined heavy industry earlier, but when I talk about heavy industry, I'm talking about, the energy sector, chemical processing, construction, mining, the railroad industry, these very large machines that are, doing all sorts of different things, but very, very, very large capital intensive machines. So, things like gears for big earth drilling machineries, custom manifolds and impellers for different chemical processing plants, nozzles for the food industry, for the food processing industry. Pumping components, heat exchangers, fuel atomizers. These are all parts, we'll talk about a lot of these today in detail, but these are all, getting your mind kind of wrapping around what some of the parts we're seeing in the heavy industry are and where some people are being successful. So let's talk a little bit about the promise of metal 3D printing. We already just talked about a lot of these, but I just want to briefly, mention these in detail again, and specifically around metal 3D printing. So the ability to rapidly prototype. And as I mentioned earlier, now we're not just prototyping for form and fit like we so commonly do in plastic, we're actually testing function. We can put our part into our machine under high heat, high corrosion, high loading environments with lots of stress and pressure, and actually see how that geometry performs. In terms of part consolidation, like I mentioned, so many parts are designed for their manufacturing method that can not, their end use application, that it's so much easy, it's so possible since we're building in an additive method to consolidate, a bunch of parts into just one component by reducing fasteners, by reducing assembly. And this really makes, parts perform better as well as simplifies the assembly process. Complex geometries. And let me clarify this a little bit too. Complex geometries have been possible, since, machining has existed, since casting has existed, since forging has existed, people have been creating complex geometries. But when I talk about complex geometries today, you're going to hear me say a lot, justifiable complex geometries. In the past, when I'm designing a part for machining, for example, I'm trying to make that part as simple as possible so it's easy to machine and it's inexpensive, to machine and it can be produced quickly. With 3D printing, it's often possible to add complexity to your part that actually reduces your part cost and it reduces the processing time. So you can imagine adding lightweighting features to a part. If we were machining that part, we now have more cuts, we have more, more material to remove. That's actually going to add to my part cost. It's going to actually add to, the lead time on that part. It's a more difficult part to machine now. But, if I remove material from, from a part that we're going to print, now there's less material that needs to be printed. We're removing costs. Now there's less material that needs to be printed again. We're removing, print time. So justifiable complex geometries. We're now able to have much, much, much more complex parts than we could justify if we were using a traditional manufacturing method because we're printing them in an additive method. Design customization. Of course, since these parts, are never involved in any tooling, you don't have to generate any tooling to produce these parts. It's very common to be able to adjust the geometry on the fly, for specific scenarios, for specific customers. So, it's as simple as just altering the geometry in your CAD system, upload it to the printer, and in a couple of days, you have that specific geometry ready to go. Rapid tooling, this idea of tooling is generally some of the most expensive and longest lead time components to create. So the ability to actually print your tooling. We won't talk too much about this today just because we're talking about heavy industry specifically, but the ability to print your tooling is something we're seeing a lot of. So things like injection mold cores, extrusion die, stamping tools, die casting inserts. Those parts are quite complex, quite expensive. They need to be made out of metal, which makes them excellent parts to print, especially since the volume is almost always low. On-demand manufacturing, we'll talk about this, a lot today, but the ability to just simply, print parts on demand when and where you need them, rather than, having to, warehouse or, or depend on a supply chain or, order, in large quantities for batching, from a foundry, for example. Now we can just, produce when and where we need it on demand. That kind of goes hand in hand with this idea of re-engineering of the supply chain. This one actually, is going to take a little bit more time to happen, but we're starting to see this happen as more and more printers are being deployed around the world. This idea of rather than sending, a hard good that maybe have been produced in Asia or, in South America, and we're shipping those products around the world, now we can just send digital files. Because if it's a part that's going to be printed, it doesn't matter if it's being printed, in Brazil or it's being printed in Russia or in Canada or the US, the part cost is going to stay the same. So, this ability that we're seeing, offices that have global, or companies that have global offices around the world, rather than sending a part to, their other office, they simply just send them the file, they print it on their printer, right there on location. Of course, this will take longer to come around as we're seeing more and more printers being deployed, but, this idea of kind of this re-engineering of the supply chain, and, we're starting to see this starting to happen. So let me talk a little bit about traditional, or what I would call traditional metal 3D printing, also known as powderbed fusion. Powderbed fusion has been around for a while. It's a method of producing parts out of metal powders, layer by layer. You're, either selectively melting or welding, these layers of fine metal powders layer by layer to actually build up your part out of this metal powder. Generally, when we look at this technology, when Desktop Metal was founded, we saw that it was generally too expensive and too slow for broad adoption. Generally, you have to spend about $1 million in capital expenditures to get a machine, and that's to produce about 1 metric ton of parts per year. The materials, they weren't very familiar materials. There's some special alloys that need to be produced for the process. There's no 4140, there's no tool steels, there's no 6061 aluminum. The cost, like I mentioned, is very high. It's a very labor, the cost of the CapEx, as well as the cost of your part. It's a very labor-intensive process. The post-processing is quite extensive. There's not a lot of automation. You need a highly trained operator who has to wear, one of these bunny suits and things like that to depowder and to remove your part from the bed. The speed is still relatively slow, like I mentioned. So don't get me wrong. Powderbed fusion is a great technology, but it's not a great technology for broad adoption. It's not an accessible technology. We're really seeing powderbed fusion being embraced by the very, very, very high-end manufacturers such as, aerospace and medical device industry. Implants are very common as well. So for the average day engineer, for the average day manufacturer, for the average day student, this is not a technology that is accessible to you. The parts costs are too high, it's too hard to use, and the equipment is too expensive. So at Desktop Metal, we thought, wouldn't it be nice if there was a way to print metal parts that was a lot more accessible? It still had this benefit of on demand. You didn't need these special facilities and operators, these highly trained, operators that I mentioned, with the special PPE protection, and it still has this broad palette of familiar materials that engineers are already used to working with. They already are using in other aspects of their design. On top of this, give engineers, a path to mass production. So if they're prototyping with 3D printing, how do they then move to higher volume? And the way that Desktop Metal did this was to build our printing systems around the chemistry and supply chain of metal injection molding. I briefly should mention, I should briefly talk about metal injection molding if you're not familiar with it, but metal injection molding is this powdered metal process. it enables you to create these very complex shapes and then mass produce them utilizing these inexpensive metal powders. It has widely accepted and validated standards, ASTM and ISO standards. It's used in almost every industry you can think of, from automotive to consumer products to firearm components to aerospace to medical as well. It enables you to create these very, very, very high detail parts out of these low cost powders. And a little bit about how metal injection molding works. Stick with me here. It's important to understand metal injection molding to understand how our printers work, because we kind of stand on the shoulders of this technology. So metal injection molding starts by creating, a feedstock. This feedstock is a combination of a metal powder, that's that low cost metal powder like a steel, and a polymer binder, which is similar to a glue. That's going to create your feedstock. You're then going to inject this feedstock into a mold to create the shape of your part, similar to what you would do in a plastic injection molding process. You're going to eject that part from the mold. What you're going to end up with a part is what we call a green part. That's that combination of metal powder and that polymer binder. It's just being held together with that binder, which is like that glue. We're then going to put it into the debinder. That's going to remove actually most of that binder out of your part. It's a solvent wash. And then we're going to go into the furnace. The furnace is going to get just below the melting temperature of the material. It's going to remove that last bit of binder, and you're going to end up with this, strong, dense metal part, high resolution part. So the issue with this technology from our perspective was this molding step. You need this large injection molding press. You need these steel molds for each different part you want to create. So, if I want to create this part today and I want to create this part tomorrow, I don't know how well you can see these, I'm going to need a different mold, right? I'm going to need these steel molds that have to be machined. They have to be wire EDM to be high tolerance. Then I have to set up the mold. And then, once I do that, I can produce the, green part every couple seconds, because it's a molding process. So, it's great for high volume, but again, not good for low volume. This tooling is just too expensive. It's too difficult to allow people to produce parts with metal injection molding in low volume. So let me introduce to you the studio system, which is, I have the printer and the furnace behind me. We also have a debinder as well. And I hope you can see where I'm going, because this technology works very similar to metal injection molding, except for we removed the actual molding step. So instead of creating this loose feedstock, that's that combination of metal powder and that binder, we're going to create a rod. That rod is that same combination, but it's fully encased in a wax. This ensures that you're never exposed to any loose powder. It's very safe to handle, and you don't require any special facilities for these rods. They're very, very safe to handle and have in an office environment. Again, remember, we're targeting accessibility here. We're really just hitting on all these points of accessibility and how we made this product easy to use. Rather than needing, the tooling now, I don't need a mold. I simply just print these rods. I print the rods layer by layer. That's that combination of metal powder and these binder, and I'm going to build up that part layer by layer to create, what comes off the printer is very similar to what would come out of the mold, except for, of course, I didn't need these molds. I didn't need this molding press. I then put my part into the debinder. I'm going to remove most of the binder out of the part, and then we put it into the furnace, where we're going to actually center our part. We're going to get just below the melting temperature of the material. We're going to get a strong, dense metal part. These are all studio parts. As you can see here, I have these strong, dense metal parts. And I'll show you some in detail under the scope here. Just quickly about the three pieces of equipment. The printer, similar to the safest and most widely used 3D printing process at FDM. This means that you're going to have familiar design guidelines. You have these office-safe materials, so there's no powder handling involved at any point during the process. The debinder, targeting accessibility, low emission design. It has this automatic fluid distillation and recycling. It's safe for an office environment. The parts go into the debinder dry, they come out of the debinder dry, meaning you're never exposed to any debind fluid. The furnace, it's really the first, office-friendly sintering furnace. It's going to fit through an office doorway. There's no residual stresses involved in the process, like those of the, laser-based system. The furnace has a peak temperature of 1400 degrees Celsius, which allows you to, sinter the wide variety of alloys to the highest densities possible. So what's the result of this process? We're getting what we call a near net shaped part. So resolution, accuracy, surface finish is similar to what you would get in a high quality casting. We're getting dimensional capabilities of about plus or minus 0.8%, but it's important to know critical dimensions can be easily achieved with post-processing. So, if you do need a tighter tolerance, you can simply put it on a mill and machine just, half a millimeter off your part, instead of having to machine this entire part out of a rock block of steel. I'll flip over to my other camera now, and you can see, I'll show you a couple different parts here, but you can see, some of the layer lines in here, but we really like to consider this, a high quality cast component, but I think they are actually a little bit better than that. Also, parts are fully compatible with mass finishing operations. So, if I need a better surface finish, for example, this part has been tumbled in an abrasive media. So simply just, throw it in the tumbler, get that nice surface finish that we need for this application. Same is true for, machining of a part. If I needed to machine, just, the inner diameter here or something, it'd be much easier to do that than to machine this entire part out of a rock block. Materials, working with a wide variety of materials, and again, familiar materials. So 17-4 stainless steel, very common stainless steel for, excellent mechanical properties. 316L, another common stainless steel, a little bit better at high temperatures and under some specific corrosion environments. Alloy 625, also known as Inconel, excellent at high temperatures, excellent in some specific corrosion environments. H13 tool steel, excellent tooling material, known for its excellent hot hardness, which makes it excellent for fluctuating temperatures, like an injection mold core. 4140, another common low alloy steel, excellent hardness, which makes it great for end effectors, housings, even sheet metal tooling is commonly made out of 4140. And then, of course, copper, your high purity copper, which is great for those thermal and electrical conductivity parts. So, quick recap, there's no hazardous powders during any point during the process. You're not required to have any respirators. There's no dangerous lasers involved in the process. You don't need any third-party equipment. There's no highly skilled dedicated operators. There's no welded supports during the process. So, we have a release layer to allow your parts to come right off the supports. And again, no special facilities required at any point during the process. So let's talk through some applications of the studio system. We'll start with the roller screw. This is a part that I have with me here today. I'll go ahead and put it under the scope here so you can see it in a little bit higher detail. But the roller screw is actually an essential component of a linear actuator. This one's actually used in a power plant for opening and closing the steam pilot valve. Hopefully I can frame this up a little bit better. There you go, it's pretty good. Okay. This part was traditionally manufactured out of 7 different components, but with the studio system, it was able to be consolidated all into just simply into one component. This part was actually able to be prototyped on the studio system. They wanted to mess with some of the threads, some of the thread profiles, the pitch, the actual geometry of the thread, etc., and then move to mass production on the shop system. So for example, on the studio system, this part can be printed for about $86, takes about 4 days. On the shop system, we can move down to just $51 per part, and you can do about 239 of them per week. So you can see that, with binder jetting, we're really moving up, the production volume. Compared to the CNC costs, about $1,900 for this part. So huge cost savings. It's going to take about 2 weeks. So we're getting, over 4 times faster, with printing process here. You can see the original design, it had 2 different gears that were manufactured separately, that then had set screws to actually attach this, and there was some Loctiting involved as well. Now we can just consolidate this all into one part and print it all together as one part. This heat exchanger, this is a helical heat exchanger. It's used in a chemical processing plant. This is a copper component. But this part actually features, two different cooling, an inlet and an outlet, and actually has a helix that runs throughout the part to actually cool a chemical in a chemical processing plant. You can see, the fins as well, the fins on this part to allow it to increase the surface area to actually increase the cooling as well. This is a really cool part. Since the part was going to be printed, they decided from the beginning, they were able to incorporate that cooling channel. They were also able to incorporate these, these external and internal fins that, would be very, very, very expensive to machine due to, their thin features, and copper can be gummy and quite expensive to machine. The studio system was able to print this part in just 4 days, about $440. It's not possible to produce this part via SOM or Powderbed fusion, but, the CNC machining alternative was about $2,100. And that's without that internal helical channel that we looked at earlier, because of course you wouldn't be able to machine that. So over 5 times cheaper, 3.5 times faster. So, a great application. And you can see it, the part being printed here, since we're printing layer by layer. It's no problem to incorporate these channels into this part. The channels were designed in a tier shape inside of the part as well, so that way they don't require any support during the printing process. Great. And you can see, the final part there after printing and, after sintering. Impellers, impellers are always the cool geometry. They kind of look like ninja stars to me. But, depending on the pumping scenario and the fluids that are being pumped, it's desirable to have, a few different impellers, and you want to optimize these vanes to ensure that you're getting optimized pressures, head pressures, and flow rates for your pumping scenario. These vanes, of course, can be very difficult and very expensive to machine. They're quite thin, they're quite organically shaped, making them quite expensive and quite complicated to machine. The impeller A that you're seeing on top here, that was produced out of 316L for its corrosion. This one here is actually used in an oil and gas environment and was made out of alloy 625 or Inconel, which gives it that excellent heat and corrosion resistance. The first impeller up there was produced for about $53, took about 4 days. This impeller that you're seeing here is about $230, takes about 5 days. It's a very cool part. Okay, hydraulic brake housing. So this is a great example of a part that was, this one actually won't fit under my scope, so I'll flip my camera back to my front-facing camera. But this is a part that was an originally cast component that then needed to be replaced. They needed a replacement part, so they needed to, find a new manufacturing method because they weren't going to go to a foundry just to produce 1 or 2 of these components. It's used for a hydraulic brake component on a large articulating truck, like a dump truck kind of. Of course, it was originally produced via casting in high volume. They then did some post machining of just some critical dimensions. So they were able to reproduce this part, via a low alloy steel at a 4140. They were able to mitigate this supply chain of casting, greatly accelerate the manufacturing lead time to replace this part. This part is quite large. It's one of the larger parts that are possible in the studio system, but takes about 11 days to produce this part. Costs about $900. But the alternative for them was, CNC machining, which is going to cost about $2,500, take about 4 weeks, and they would have to go out of house. So just a great, this is a cool big part. Cool. We will move on. Let's move over to binder jetting and talk about the shop system. So the shop system is really the world's first metal binder jetting system that's designed specifically for machine shops. What does this mean? It means that it's accessible for all, meaning in terms of cost and ease of use, which hasn't necessarily been true for binder jetting in the past. It has this unparalleled productivity, meaning it produces parts very, very quickly and in high volumes, and then that you would expect for a machine shop. Then you're getting this very, very, very high print quality that you would expect to get out of a machine shop. You're getting these high quality parts that a machine shop would be happy to put their name on and produce as their parts. So binder jetting is possible for mass production. We already learned to use these metal injection molding powders that are, that we already use in this process as well. And now we're learning to use them with the binder jetting process. Both of these processes rely on these low-cost metal injection molding powders, and then we use this organic binder that's going to be removed and sintered in the furnace. So a little bit about how binder jetting works. Binder jetting is a powdered metal process. I should mention that. So you start with a loose powder on the right in the build box. You're going to spread just a thin layer of that powder across the build box, about 50 microns thick, to create your layer of powders. Think of it similar to a sheet of paper. You're then going to have your print head come across and actually just jet that binder onto that layer of powder. So rather than mixing the binder and the powder together and then printing it, here we're first spreading the powder and then we're just jetting binder where our part layer is. So in this example, our jigsaw puzzle pieces here are our parts that we're printing, and then this print head's going to come across and jet binder just on the locations of the the jigsaw puzzle pieces. This allows us to print an entire layer in just a few seconds, very, very quickly, because this print head just comes across similar to an inkjet printer and just jets that binder across that layer. We're going to move the build box down a layer, spread another layer of powder, and the binder, and the print head's going to come across again and jet another layer of binder. After printing is complete, you're going to take out your build box. You're going to have to depowder it because it's going to be a solid cake of powder. You're going to remove all your parts from that, shake out all the loose powder, which can then be recycled for another print job. You're going to put your printed parts into the furnace because at that point they're just held together with the binder. The furnace is first going to do a thermal debind where it's going to remove that last bit the binder out of your part, and then get up just below the melting temperature of the material to actually sinter the part into a strong, dense metal part. You can see I have some binder jet parts with me here today, and these are nice steel parts, and I'll show you some in high detail under the scope. So important to know, creating a wide variety of different geometries, but now we're moving to some higher volumes. All these parts are, just to give you an example of tons of different parts that have been printed, but it's important to note, all these parts have been printed without tooling. And now we're moving to hundreds of parts per week, thousands of parts per week. So now we're actually unlocking the potential to do, mid to low volume runs without the need for any tooling, which is really, really impressive, and, allows for, a lot of, cost breakdowns as well as, lead time acceleration. So, for example, if you look at this build box that's here on the right, this is an example of a 16-liter shop build box, and you can see all those different geometries that are inside of that build box. Imagine asking your machinist or going to a machine shop and asking you to produce each one of those different geometries, ask them to produce each one of those different geometries for you. They would have to have lots of different machines set up, lots of different operations, tons of different programming for different mills and different CAM softwares. You'd have to cut lots of different stock. You'd have to create tons of different fixturing to produce these parts. It would be very, very difficult. It would take them a long time. You can print that entire 16-liter build box, overnight. The next day the parts are ready to go into the furnace, and in just a few days you have, hundreds of different geometries if you want, tons of different parts. So this allows us to, really, really accelerate, lead times because we're able to create lots of these different geometries very easily and very quickly. At the same time, you can also use it for like those higher volumes that I mentioned, where we're printing the same part, hundreds of copies of that same part without the need for tooling. This allows us to really reduce costs with the shop system. Of course, we're eliminating tooling, so we're printing our parts without the need for molds or work holding fixtures that are going to add to our part costs. We're reducing our tool wear because generally we're just machining critical dimensions if even necessary. We're greatly reducing our labor costs. We don't need to scale our machinist time with the number of parts. We can set up that entire build in just 1 to 2 hours, regardless of the complexity, compared to hours of a machinist time per part to set up that manufacturing operation. We're greatly reducing the number of manufacturing steps involved because we're printing our part to that near net shape. We're still getting that plus or minus 0.8%, and then if necessary, we're just machining any critical dimensions, a hole or a surface, something like that. It's quite common with 3D printing to talk about reducing costs, but with the shop system, it's actually possible now to increase revenue. So if you are a machine shop, the system is designed, for machine shops or those environments. You can now produce these previously unattainable geometries, things that just wouldn't have been possible before: assembly consolidation, design optimization, beyond what's possible with CNC machining. This means, you have new technology to offer to your customers. You can print parts that you wouldn't have been able to do before. You can print these hard to machine materials like tool steels and super alloys that are quite expensive and quite difficult for you to machine. You can make these smaller and medium-sized jobs economically viable. In the past, you may have had to say no bid because you would have had to invest too much into the fixturing or the tooling, but now I can just throw them onto the printer overnight and then, ship them out to the customer very quickly. We can win some new business, because we're able to improve, we're able to improve our, our cost equations. The part cost is going to stay the same, and then in general, if we're in a machine shop, we're able to offload, a lot of work onto our shop system and allow the CNCs to work on just different jobs, really opening up some throughput in our shop. So let's look at some applications of the shop system. Downhole tool slip. This is a part used in oil and gas operations. I have this part with me here today, or one of them with me here today, so I'll show you this in detail. These parts actually do have a little bit better surface finish than the studio parts. Let me see, like, if I can, yeah, you can see a little bit in detail, but I'll flip it so you can see the whole part here. Great. This is a part that actually, they were doing quite a bit of R&D work on. You can see they have a couple different patents for different tool slip geometries that they were working on. But this part is used for holding, using a frictional hold between a frac plug and a pre-existing pipe that they drilled. So this is another great example of a part that they were able to prototype on the studio system, and they're actually able to test all these different face geometries to optimize the hold for these different pumping scenarios. It's a great example where, plastic would not have sufficed. The parts needed to be under high loading, high heat, even in these corrosion environments, these very dirty working environments where they're pumping out oil. So, a plastic part would not have sufficed for prototyping. So they were able to use the studio system for their prototyping, functionally test these components, and then actually move to mass production on the shop system. So the studio system, each one of these could be produced for about $95, taking about 5 days. This is out of 17.4 stainless steel. And then moving to the shop system costs about $81, but we can do about 200 of these parts per week. So we're still seeing, a big cost savings and a big lead time savings over the CNC alternative for this company, which was about $278, taking about 2 weeks. Bulb nozzle. This is a part that's used, as you can probably get why it's called that. It's used in a chemical processing plant for spraying a gas. Traditionally, this part was actually cast, followed by some extensive secondary machining of some of this geometry, as well as the bottom threads that are on this part here. Hopefully you can see that. But those threads are printed right into the part. The part need to be manufactured in a quantity of about 100 of these. So rather than having to go to a foundry, wait that long lead time, and then also the post machining, they were able to print the entire order of nozzles in just in less than a week. After printing, the only operation that was required was they actually just did a secondary tapping of this thread. The thread is printed in, but just to tap it again, just to ensure that it's it's going to be a tight fit, just to kind of clean up and chase those threads. But I don't know about all of you, but I don't know if you've ever tapped steel before. It's not a fun thing to do. So by printing it in, it makes it much easier to clean up those threads rather than tapping it out of a raw material. Shop system, each one of these can be produced for about $29, do about 319 of these per week. SOM, which is that Powderbed fusion process, was going to be about $376, taking 2 to 3 weeks. And CNC machining was about $84 after the casting process and taking about a month. So huge cost savings, huge lead time savings, as we've seen a lot today. Sensor holder. This is another part that I have with me here today. I think I have almost all the parts we're going to talk about. But this part is used for holding multiple different sensors in a precise location to take different measurements on a running machine. The small details on this part would make it very, very difficult to machine, as well as some of the overhangs that are featured here. It would also be incredibly difficult to metal injection mold because some of these overhangs would require live action tooling and sliders of that nature. Printing on the shop system allowed it to be printed with greatly accelerated manufacturing lead time, as well as a reduced part cost. So this part was able to be produced for just $7.80 each. You can do about 1,500 of these parts per week. Another thing that I should have mentioned earlier, but since we're able to print these parts without tooling, we can now change these parts whenever we want to. So if we need to incorporate different sensors, all I have to do is make some adjustments to my model in my CAD system, send them over to the printer, and that night I can print a couple hundred of those. It makes it very, very easy, very, very accessible to make changes to your design, which mitigates a lot of risk. Because I'm not spending tens of thousands or thousands of dollars on tooling that, my design better be right if I'm about to spend that much money on tooling. But here, I can move quickly, I can make changes as I go. It's very, very easy to just make a change to your part, send it back to the printer, and we're ready to go. Cool. Keep moving here. Bearing housing. This part is really, a great part that showcases the accessibility feature of this system. So this part is used to hold some press fit bearings in a precise location in a machine. The company here needed this part to be produced quickly and out of steel. Using the shop system, they were able to print all the parts that they were going to need for the machine in just 2 days, and they were ready for assembly in less than a week. So, here we're, talking about accessibility. Manufacturing required almost no operator labor. It greatly accelerated the manufacturing lead time to produce this part. And then, a large cost savings compared to, doing rush machining job or, a rushed fabrication job from a service bureau. Shop system here, able to produce this part for about $73. And it can do about 192 of these per week. CNC machining, was about $162, and that was for 2 weeks. The rush job was, well over $400, $500 per part. So big cost savings as well as lead time savings here for this bearing housing. So let's switch over to talking about some case studies. We've looked at a lot of applications, we looked at a lot of parts, but let's talk about some of our customers, how they're using the system, how they're adding value, both from a part perspective as well as from a business case. Why do they purchase the system? What are they looking to use it for, and how are they being successful? Okay, Master Drilling. Master Drilling is located down in Johannesburg, South Africa. They are a manufacturer of these very, very, very large earth drilling machines, mostly used for the mining, energy sector. They drill miles into the ground for, oil and gas operations, mining operations, a lot of gold down in South Africa. These huge, huge, huge machines with drills that, it's pretty impressive how deep they're able to drill with these things. One part that we're going to be talking about today is this sun gear. This sun gear is attached to a planetary gear set. It attaches to the motor that attaches to the actual drill bit that does the drilling, deep into the ground. Unfortunately for Master Drilling, this part was originally produced in a foundry in China. It was taking them about 3 months to get each one of these parts, and unfortunately they had one of them break. So what they needed to do was, of course, replace this part as quickly as possible to get this drill back up and running, to get their mining operation back up and running. Because every day this drill is sitting idle, it's not good for them. They're losing money, and the drill is down. So by using the studio system, in just 3 weeks, we're able to print the part, debind the part, sinter the part. They then did some post machining of the part and a case hardening operation just to increase that hardness value, and end up with this end use part that I have with me here today. So the result is going from a 3-month lead time down to just a 3-week lead time with the studio system. So this is a great example of that replacement part, able to get this drill back up and running, drilling, rather than having to wait 3 months or finding another manufacturing method to produce this part. As the part came out of the furnace, it was about a 25 Rockwell. After the heat treatment process, they got it up to a 43, which is important for this gear component. And they even did a plasma nitriding process to get it up to 64. So just another great example of a replacement part for the heavy industry, around that mining operations. And you can see it here. It's quite a large part. You can see the quarter on screen here. It's quite an impressive large part. Okay, let's talk about Ewall. Ewall is located in Italy. They're founded in 1967. They're a leading vendor of high-tech marine propellers, mostly for sailing yachts. They use a wide variety of different stainless steels for, their accuracy, performance, mechanical, and corrosion resistance. So they were happy to see that Desktop Metal was already offering a lot of materials that they're familiar with working with. So 2 key areas for the studio system. We're talking today about, the propeller pinion. This part is used to connect the propeller shaft to the blades, and the goal here was really to streamline their manufacturability. So this part is traditionally made from investment casting out of 17.4 pH stainless steel. So the goal here is to overcome these investment casting manufacturing constraints. So generally they had this minimum casting lot size of 100 pieces. If they weren't able to, order a minimum order of 100 pieces, they had to collect other jobs. They had to wait until the lot got big enough. Even after they placed an order, there was still quite a long manufacturing lead time. Investment casting is a great process, but it takes some time. There's alloy procurement, alloy procurement. They have to set up the wax patterns. You have to coat it. Then you actually have to do the actual, the casting process. And even after they got the parts back from the foundry, they still required some challenging, labor-intensive CNC machining. They had to CNC machine those inner ribs that you're seeing here. The cutting tool also had to come down deep down on the internal diameter of this part, which was quite challenging. So what do? They printed this part. You can see a couple different printed iterations here. On the left there, on the right, you can see the part off the printer. On the left is out of the furnace. I should have mentioned the parts do shrink in the furnace about 20%. That's just from sintering, but that shrink is fully calculated and controlled by our software. You don't have to worry about that shrink. We account for that with our software that comes with the printer. So what was the result here? Really a more efficient manufacturing operation with the studio system. They can now be more responsive to customer demands. They have a faster manufacturing process with reduced health hazards. You know, it's much less demanding in terms of logistics. They don't have this maximum lot sizing constraints. They don't have to worry about this outsized source for these low volume parts. They're able to lower the part cost, actually improve the part quality. It's much less labor intensive, and they're actually finding it more sustainable than casting. So the big business impact, you know, with the studio system, they're really demonstrating the feasibility of additive manufacturing, you know, in terms of speed, flexibility, quality, and cost, that metal 3D printing is a real manufacturing method that they should be considering for producing these lower volume parts. They're so happy with their parts, they're actually looking to move to some higher volumes as well with the shop system. You know, being able to produce, you know, instead of actually having to go to the foundry at all, even when they move to higher volumes, they'd love to be able to take manufacturing into their own hands, produce them, you know, on the shop system in higher volumes, higher, you know, and high quality parts. Cifarelli, located in Italy. Cifarelli was founded in 1967. They're a leading vendor of agriculture and gardening equipment. They have a rich history of technology and product innovation, so they're really looking to incorporate 3D printing across their entire line. The part we're going to be talking about today is this shaker hook. This shaker hook vibrates about 2,000 times per minute, has a stroke of about 62 millimeter, and is used for harvesting nuts and olives. The shaker hook can collect, you know, over 3,000 kilograms of olives per day with a falling rate of 95%. That means it's going to be able to get 95% of the fruit off the tree without damaging the tree or any of its buds. Generally, this shaker hook was being produced via aluminum chill casting in quantities of a few thousands. But they do get some requests for these custom low volume applications. Of course, you know, these parts cannot be produced economically in lower volumes via aluminum casting because, you know, the tooling's too expensive. Going to the foundry, they have those same lot size and constraints. It just makes it not possible. So here, the goal with 3D printing was to see, can we produce these, you know, these shaker hooks in lower volume with the studio system to, you know, allow us to be more, you know, more agile to customer demands. One thing they realized, though, when they switched to the studio system was that now they were going to be printing the part with steel. The studio system does not print aluminum, and the original parts were printed in or were manufactured in aluminum. So since they were moving to steel, they needed a new design. And they were very smart about it because they realized that they were going to be printing this part. So they were able to leverage some generative design software. The generative design software, we're going to apply our loading, we're going to apply our frequency of the shaking, we're going to put all our constraints in, and we're going to allow the software to design the part for us. We're going to end up with this very organic shape like you're seeing on the right that generally is not very easy to manufacture via casting or machining, but it's very, very suitable for 3D printing. So the result was some shaker hooks that are actually lighter than the aluminum original, but actually stronger than the aluminum original as well. So they're actually able to leverage that strength of steel and also leverage this generative design software. You can see two printed shaker hooks here on the screen, and you can see it actually attached to the shaker here. And so the big business impacts for Cifarelli, you know, this ability to create a part that's the same weight but much stronger. So, you know, generating, you know, these generative design softwares for these low volume applications. And this is a great example of this justifiable complexity that I mentioned earlier. Since we're going to be printing the parts, we're going to be doing an additive nature. We can afford to do these organic shapes. We can afford to do these, you know, these lightweighting features because they're not going to significantly or even, they may even reduce the cost of our part. They're really finding this, again, you know, game changer for new applications, looking to incorporate this across all their product lines for these lower volume production parts, and in the future, looking, you know, to move to higher volumes as well with the shop system. John's Inc. Hand-Wheeled Combustion, located out in Oklahoma. They are a leading vendor of emissions control and clean air combustion systems. As emission standards are becoming more and more stringent, John's Inc. offers a wide range of capabilities to help with these combustion processes, to help with emissions control systems. They had an additive manufacturing initiative that they rolled out in 2016, and luckily that included desktop metal. So their additive manufacturing initiative started with 13 Ultimaker S5s, which are relatively inexpensive plastic printers, and they strategically located them at a bunch of their different offices around the globe. And they encouraged their employees to print not just work-related parts, but also personal parts. You know, they wanted to get their employees familiar with 3D printing, using 3D printing, because they really saw the value, and they wanted to get their, you know, their engineers and their designers used to designing for 3D printing. They then purchased a desktop metal studio system, and they got up and running printing metal. So what is Johns Inc. using their studio system for? They're printing lots of jigs, fixtures, custom tools, and dies. They do have quite a large fabrication shop and manufacturing shop there on site in Oklahoma. So, printing a lot of their tooling for that shop is great. Urgent aftermarket orders that require parts sooner than they could receive them from their casting suppliers. They're doing prototyping for testing purposes, to allow them to actually test parts. A lot of these parts are burner components under high heat to allow them to actually prototype these parts and actually test them in the actual environment. And then actually doing some parts that could not be manufactured with traditional manufacturing methods. We'll talk about this atomizer in a second that features some channels that just couldn't be made any other way than 3D printing. So let's talk about this atomizer now, actually. So this is an atomizer that's used in a marine burner for steam propulsion on a liquid natural gas tanker. It mixes steam and fuel in the burner to allow it to burn and actually power this boat forward. The problem with the original atomizer that you're seeing here, it's a very simple design, was that during low load, it got a very poor burner turn down of just 15:1. So what does that actually mean? That means that when this ship was going slowly, when the load on the engine was low, when it was maneuvering in port, when it was putzing around in the harbor, it got very, very, very poor fuel efficiency. So Johns Inc. was tasked with how do we increase the fuel efficiency of this ship? And of course, they targeted this atomizer. This atomizer needs to be redesigned. They very quickly came up with a variety of different designs, and they very quickly realized that by altering the shape of this internal channel, by altering some of the curvatures and some of the the actual hole patterns, they're able to increase that performance of mixing of that steam and that fuel. And they very quickly realized that by using additive manufacturing, they were going to be able to have the widest variety of options. Of course, since this is a burner part, under high heat and some corrosion, this part needed to be prototyped in metal. You can see a couple different iterations here, and then the journey to the final design, which is the part that I have with me here today. I'll flip over to the overhead camera here, but this part was produced in 316L to give it that excellent mechanical properties, especially at high temperatures. Utilizing 3D printing, they're able to radically redesign this part. You can see sort of the teardrop oblique or oblong, I don't know that word, the teardrop kind of holes in the part here. And then actually, if you flip over to the bottom here, you can see there's actually, where the steam and fuel are actually going to be mixing. These holes kind of helix up through the part into the top of this part. This is a part that couldn't be produced any other way besides, metal 3D printing. They were able to improve this burner turn down from 15:1 all the way up to 25:1. So that was a 67% improvement. And what that ultimately resulted in was about a $90,000 to $160,000 fuel savings for their customer annually. Studio system version cost about $300 to print this part. Took about 5 days. Via DMLS or Powderbed Fusion, which they also looked into, it was about $1,200. Took about 8 days. Great part. And you can see it actually firing here. As you can imagine, very, very hot in there, so it needs to be made out of metal. Another example here. So Johns Inc. did some work on the USS Blue Ridge on some safety devices. The ship needed some replacements for these yokes and handles for the safety setup device. The parts were originally cast, but of course that foundry no longer has the tooling or no longer is even existing, or they lost contact with that foundry. It's much easier for them just to pull the files, throw them on their printer, and in a couple of days, they have these end-use parts ready to ship out to the USS Blue Ridge to be installed. This part here, I'll switch back to my camera just because this is quite a large part, but this is another burner component. This is YE6 burner tip. If you look at this drawing here, this drawing was originally produced in 1967 for a foundry. This part was originally produced in a foundry, and of course, Johns Inc. got a request for replacement of one of these parts. The heavy industries, these machines are expected to last a long time. Let me see if I can get this under my scope. It's a little bit of a big part, but. So, rather than finding a foundry to reproduce this part, Johns Inc. was able to just, they actually had to model it because the model didn't even exist of the part before because it was produced in 1967. They were able to throw it onto the printer, print this part in a little over a week and ship it out to the customer. So a great example of how we can use 3D printing for these urgent aftermarket orders, especially when we want to avoid a casting supply chain, which is, can be 6 to 8 weeks, no problem. So this part was able to be produced for about $193, took about 7 days. The SOM alternative, this part actually cannot be produced with CNC machining because of some of the undercuts in here, was about $6,600 just because it's so large. So, a great example is also produced in 316L for that heat resistance of a great studio part for those urgent aftermarket orders. So big business impact for Johns Inc. They were familiar with Powderbed Fusion in the past. They had used some of those, that high cost laser Powderbed Fusion process. But now that they have this lower cost metal 3D printing and they have it in-house, it's opening up so many new designs for them, so many new opportunities to simply just throw the part on the printer and get this nice complex metal part in just a few days. They're able to take new designs to market faster by testing multiple different design iterations, all without the need for tooling. They're avoiding their tooling for their low volume parts, and they're getting a much faster turnaround than they would from casting houses when they need to, when they need to produce a part that was originally cast or maybe designed for casting. So that's all I have for you today. I really appreciate you taking time out of your day to join me, talk about additive manufacturing. I always like doing these webinars, but I'd love to take it one step further. I'd love to meet with one of you one-on-one, or all of you, or anyone who's interested, one-on-one, to explore how metal 3D printing can work for your business. I'm happy to look at some of your parts. If you want to send me step files, I'll give you my email here in a minute. I'm happy to give you part assessments. I can tell you how much a part would cost, how long it would take, whether or not I think it's a good part for the system. And of course, free part samples if things are looking good. This is a great opportunity. Not a lot of pressure. If you want to join one of these meetings, I'm happy just to talk with anyone here about additive manufacturing, where you think it can add value, maybe specific to your industry, to look at some of your parts and let you know if these systems could be a good fit for you. You'll receive an email after this webinar with a link to a recording, as well as the slides, and an opportunity to sign up for one of these webinars or one of these one-on-one meetings with me if you're interested in chatting more. Thanks so much again. I really appreciate you taking time out of your day to join me. It's always good to talk about additive manufacturing and 3D printing. I hope you learned something. I hope you got to see some cool parts that related to you. Like I said, feel free to send me an email if you have any thoughts, questions, comments. I'm happy to chat with anyone on here, either in person or over email if you want to send me files or etc. All right, thanks again, everyone.